So here electromagnetic force. So in this video again after a lot of consecutive formula. So here executing a electromagnetic force. So the electromagnetic force, the EMF of a source may be defined as the work done by the source in taking a unit positive charge from a lower potential terminal to the higher potential terminal, or it is the energy supplied by the source taking per unit positive charge. Okay, and unit positive charge, and once round to the circle, once complete the circuit, it is equal to the terminal open potential difference measured is open circuit. So basically EMF, an electromotive force, is equal to work done divided by charge. Okay, work done divided by charge. Oh, it is equal to W by Q. So this is the things. Okay, and for the definition it will write as the direction of motion, the direction of motion. Okay, the direction of motion of positive positive charges is taken as the direction of the conventional current is taken as the direction of the conventional current is taken as that the conventional current. So electron is negative is taken as that the conventional current. Okay, and and the source may be defined as source may be defined as the work done by the source, the work done by the source. Yes, work done by the source. So the work done and in taking a unit positive charge from lower potential terminal, in taking a unit positive charge from lower potential, from in positive lower potential. Okay, charge from lower potential to the higher potential terminal, to the higher potential charge to the higher potential terminal, or it is the energy supplied by the source, or it is the energy supplied by the source. Okay, by the source. So this is the electromagnetic force. So SI unit, now come to the point. SI unit of EMF is volt. SI unit of EMF, yani electromagnetic force, is what is volt. Okay, is volt. SI unit of EMF is volt. Okay, an electrochemical cell is supplies energy if if an electrochemical cell supplies energy of 1 joule, okay, for the follow of 1 coulomb of charge, for the follow of 1 coulomb of for the flow of 1 coulomb charge through the whole circuit, through the whole circuit. Okay, so through the মানে 1 coulomb charge through the whole circuit, then its EMF is said to be 1 volt. Then its EMF is said to be 1 volt. Okay, volt said to be 1 volt. It is clear. What is 1 volt? Now, an electrochemical cell supplied energy 1 joule for the flow of 1 coulomb of charge through the whole circuit, including the cell. So then its EMF is said to be 1 volt. Okay. So second is Ohm's law. 7. Ohm's law. What is the Ohm's law? The current flowing through a conductor is directly proportional to the potential difference across the end. The current flowing through a conductor the current through flowing a conductor is directly proportional to potential difference is directly proportional to the potential difference. Okay, directly proportional to the potential difference মানে across its ends okay, provide the temperature and other physical condition. Provide the temperature and other physical condition remain unchanged. Okay, remain unchanged. So okay, so B proportional to I, or V is equal to IR. Okay, or R is equal to V divided by I. Here R is the called resistance of the conductor. Here R is called resistance of the conductor. Clear? Resistance of the conductor. So Ohm's law, the current flowing through a conductor is directly proportional to the potential difference across its. Okay, and the provide temperature. Okay, and other physical condition is required to match. So B is proportionality and potential difference is proportionality to the current. Okay, current. So V is equal to IR. So what is the resistance? 8. What is the resistance? What will be the resistance? So resistance, it is the property by virtue of which a conductor opposes the flow of charges through it, and it is equal to the ratio of potential difference applied across the conductor to the current flowing through it, and it depends on the length L and the area of the cross section A of the conductor. Okay, and through the relation, so through the relation it will be R is equal to rho into L by A. Rho is equal to resistivity of the material. Resistance, it is the the property property it is the by virtue of which A conductor oppose the follow. A conductor oppose. A conductor oppose. A conductor is directly. A conductor oppose the follow of charges. The follow of charges. Okay. Through it. Okay. Through it. Follow of conductor through it. It is equal to the ratio of potential difference. It is equal to the ratio of potential difference. The ratio of the potential difference. Okay, it is equal to the ratio of the potential difference applied across the conductor to be the current following. Applied across to the conductor. Applied across to the conductor to the current following through it. To the current following. The current flowing through it. Okay, to the current flowing through it. Uh, and it is depend on the length L and area of the cross section, and it depends on the length area of the cross section, area of the cross section. Okay, it's depend on the area of the cross section A of the conductor length through the relation of the conductor length through the relation. Okay, so of the conductor length through the relation. So resistance, it is the property which a conductor opposed to follow of electric charges through it is and equal to the ratio of the potential difference and applied across to the conductor and the current flowing through the it, and it's depend on the length of area conductor relation, and A is the conductor length through the relation. Okay, so definitely it will be R is equal to rho by A. Okay, R is equal to rho L by A, where rho it's depend on what's resistivity of the material. Resistivity of the material. Of the material. Okay, so it's depend on the resistivity of the material. Now SI unit of resistance is important point. SI unit of the resistance is SI unit of resistance is ohm. Okay, SI unit of resistance is ohm. The resistance of conductor is 1 ohm if a current of a ampere flowing through it on applying potential difference of 1 volt across its end. Okay, then what it will be? The resistance of a conductor is 1 ohm. The resistance of a conductor, the resistance of a conductor is 1 ohm, is 1. Okay, is 1 ohm. If a current of 1 ampere, current one ampere, okay, if a current of 1 ampere, uh, 1 ampere follow through it on applying potential, follow through it on applying potential through it, applying potential difference of volt across the end, potential difference of 1 volt, 1 volt across its end. across its ends. Okay, so 1 ohm is equal to 1 volt divided by 1 ampere. Okay, so 1 ohm is basically 1 volt divided by 1 ampere. So what it will be, 1 ohm is equal to 1 volt per ampere inverse. So this will be the ultimate thing. Okay, so the resistance of conductor is 1 ohm is if a current of the resistance 1 ohm volt. Okay, volt by ampere is equal to 1 ohm. So the resistance of conductor is 1 ohm. If a current of 1 ampere follow through on a applied potential difference of the 1 volt, then 1 volt across its ends. Okay, 1 volt across its ends, so then it is called 1 ampere. Clear it is. Now the resistivity of a specific resistance. Now resistivity of a specific resistivity resistivity of a specific resistance specific so the resistivity of a specific resistance. What is the resistivity of a specific? It is the resistance offered by a unit. It is the resistance offered by a unit. It is the resistance offered by a unit cube of material of conductor. Cube of material of conductor. Okay, cube of material of conductor. So it is the resistance specific in cube material. So rho is equal to ra divided by L, where SI unit of rho is ohm meter. So SI unit of rho is basically ohm meter. SI unit of rho is basically ohm meter. It is clear. So it depends on the nature of the material of the conductor and the physical condition like temperature and pressure. So it depends. On the nature of the material, on the nature of the material. Because it is depend on the nature of the material of the conductor of the of the conductor and the physical condition like and the physical condition like temperature and pressure. Physical condition, it's depend on the nature of the material like conductor of the physical condition like the temperature and pressure and temperature. Okay, then the second point is current density. What is the current density and how you will define for? So it is the amount of charge following per second per unit area normal to the follow of charge, and it is the vector quantity having the same direction as that of the motion of the positive charge. It is the amount of charge, okay, following per second per unit area charge current density. it is the amount of charge, okay, it is the amount of charge following per second per unit area per second per unit area. Okay, following per second per unit area normal to the follow of charge, normal to the follow of charge. Okay, normal to the flow of charge it is a vector quantity, then it is a vector quantity. Okay, it is a vector quantity having the same direction, having the same having the same direction as that of the motion of the positive charge, as that of the motion of the positive charge, as that motion of the positive charge. So the normal follow up, so for normal follow up charge, so normal follow up, so the normal follow up charge, basically J is equal to Q divided by T to area A. So Q by T is basically L by A. So this is the, so charge density is basically J is equal to L by A. It means that it is the current, it is the amount of charge following per second per unit area normal to the follow up charges, and then it is a vector quantity having the same direction as that of the motion of positive charge. Okay, so current density rho mane basically resistivity is basically Ra divided by L, and charge density is basically La. Okay, in general, in general uh, in general, basically I is equal to Ja cos theta. Okay, so J of J vector A vector J cos theta. Conductance, so conductance is basically, oh, what is the conductance? Next topic is conductance. Okay, so conductance is equal to 1 by resistance, 1 by resistance. So conductance is basically 1 by resistance, and Z is equal to 1 by R. Z is equal to 1 by SI unit for conductance is ohm. So SI unit for conductance, SI unit for conductance is basically ohms inverse 1. Okay, ohm inverse 1, ohm inverse जिसको ohm, and conductivity of a specific conductivity is equal to, at the same time, same topic, conductivity is equal to 1 by resistivity. So what is the conductivity is equal to 1 by resistivity? So sigma is equal to 1 by rho. So this is J is equal to sigma E. It will prove in later on. Okay, so here you can say that sigma is equal to 1 by rho, conductivity is equal to 1 by rho, and we will later and prove on. Okay, so conductivity is basically 1 by resistivity. So SI unit of conductivity is equal to ohm inverse and meter inverse. So SI unit will be ohm inverse or meter inverse. Okay, or centimeter inverse. Oh, sorry, ohm inverse or meter inverse. Okay, so ohms is equal to, this is mohm also. Sorry, mohm, MHO, mohm also. So mohm meter inverse. This will be the ultimate unit. So it will be the conductivity unit. Okay, and resistivities of different substance metals have a low resistivity in the range of 10 to the power minus 8 ohm meter, okay, to 10 to the power minus 6 ohm meter. Insulator have the resistivity is more than 10 to the power 4 ohm meter. So semiconductor have intermediate resistivities lying between 10 to the power minus 6 to 10 to the power minus 4. So why মানে semiconductor main topic is the main difference from the metal and the low মানে metal have low resistivities, okay, in the range of 10 to the power minus 8 ohm meter to 10 to the power minus 6 ohm meter. Insulator have the resistivities is more than 10 to the power 4 ohm meters, okay, and semiconductor have intermediate resistivities, okay, and lying between 10 to the power minus 6 ohm meter to 10 to the power 4 ohm meter. So resistivities of the different substance, resistivities of different substance, different resistivities of different substance. Basically metals have low resistivities, metal have low resistivities, metal has low resistivities, okay, in the range of 10 to the power minus 8, in the range of 10 to the power minus 8, okay, 10 to the power is minus 8 ohm meter, okay, and to 10 to the power to 10 to the power minus 6 ohm meter, ohm meter there. So insulator have the relatives more than 10 to the power 4 ohm meter, and semiconductor have 10 to the power 10. So insulator have more than insulator have more than the resistivity more than 10 to the power minus 6, 10 to the power 4, okay. So 10 to the power 4 ohm meter, insulator 10 to the power 4 ohm meter. Semiconductor have intermediate resistivities lying say that between 10 to the power minus 6 ohm meter to 10 to the power minus 4, 10 to the power 4. Semiconductor lies um, resistivity, intermediate resistance, okay, intermediate resistivity, which lies between 10 to the power minus 6 to 10 to the power minus 4, okay, ohm meter, 10 to the power 4 ohm meter. And for and for the color, how you will judge a resistance by color, okay. So so from the color, let's say there is a given there is a resistance, okay, and which given that the color, okay, we have seen that you have to say, judge by them by color. So then definitely what you will do, so definitely you have to first first you have to take that in black. Black is, so black is represented as a number 0 first number, and it's MLT into the 0, okay. And after the brown it will be 1, and it will be 1, it will be 2, and it will be 2, and so it will also multiplied by 6, right, let when it was 7, and gray gray is multiplied with the so electrons are positively ionized, okay. And after that, the average velocity of acquired the free electrons, okay. So for the charged ions are the charged carriers. Charged ions are electrons, okay. And positively electrons and positively charged ions, and positively charged ions, positively charged ions, what they are saying, positively charged ions are mhm. Okay. And after the charge ions are the charge carriers, are the charge are the charge carrier, okay, are the charge carrier. And in electrolytes, in in electrolyte, both positive and negative ions, both positive and negative ions, both positive and negative ions are the charge carriers, are the charge charge carrier, okay. In the semiconductor like germanium and silicon, in the semiconductor like germanium, and silicon, okay, like germanium and silicon, okay. Conduction is due to electrons and hole. Conduction like due to due to electron and holes, okay. Conduction like due to electrons and holes. A hole is a vacant state from which a electron has been removed and act as a positive charge carrier. An hole is a vacant state. A hole is a hole is a vacant state, okay. Hole is what? Hole is a vacant state, okay. A hole is a vacant state. Remember my word, that a hole is a vacant state from which an electron from from which electron has been removed, has been removed and act as a positive charge carrier, and act as a positive charge carrier, okay, and act as a positive charge carrier. Drift velocity and relaxation time. What now the second point is drift velocity. Drift velocity. What do you mean by drift velocity and relaxation time? And relaxation time, okay. What do you mean by drift velocity and relaxation time? So the average velocity acquired by the free electron, the average velocity acquired the average velocity acquired by the free electrons, by the free electrons, okay. The free electrons of a conductor in opposite direction, free electrons of a conductor, okay, of a conductor in the opposite direction, in the opposite direction of the extremely applied electric field, of the extremely extremely applied electronic field is called drift velocity. Extremely applied field is called drift velocity. Drift velocity. So applied field is called drift. So if asked that what is the drift velocity? The average drift velocity acquired by the free electrons of the conductor, okay, in the opposite direction of the extremely applied electric field, and electric field is called the drift velocity. So the average time that so the average time so the average time that elapsed between two successive oscillator between two successive of an electron of an electrons, okay, electrons is called relaxation time. It's called mm, it's called relaxation time, okay, it's called relaxation time. And जैसे कि for VD is equal to E tau divided by M, okay, and for R is equal to basically ML divided by N square tau A, N square tau A. So N square tau A, and rho is basically M divided by N square tau, rho divided by M square tau. Here M here 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 basically N is equal to number of free electrons per unit volume. Number of free number of free electrons per unit volume. Okay, number of electrons per unit volume, or free electron density, and free electron density and free electron density. Okay, and what do you mean the free electron density? What is the free electron density? So mass of an electron, basically free electron density is equal to mass of an electron. Mass of an electron is called free electron density. Is it clear that free electron density? Okay, and now come to the point, other form of Ohm's law. 18 other form of Ohm's law. What is the other form of Ohm's law? In terms of the factor quantities like current and density J and electric field A, Ohm's law may be expressed as J is equal to sigma A, okay, or E is equal to rho J. The equation E is equal to rho J leads to another the statement of Ohm's law. A conducting material obeys that the Ohm's law when the resistivity of the material does not depend on the magnitude and the direction of the applied electric field. So in terms of the vector quantities like current density J, in terms of the vector quantities like current density J and the electric field E, Ohm's law may be expressed as J is equal to sigma E. Okay, let's say we already discussed in later that in terms of vector quantity, in terms of the vector quantity, okay, like current density J and electric field E, like density current density J and current density J, okay, and electric field E, density J and electric field E. Ohm's law may be expressed as Ohm's law may be expressed as Ohm law, may be expressed as Ohm's law, may be expressed as um, J is equal to sigma E. Okay, J is equal to sigma E, or E is equal to rho J, or E is equal to rho J. The question E is equal to rho J. Basically, what is depends leads to another state of Ohm's law, leads to another state of Ohm's law, leads to another state of Ohm's law. When the resistivity of the material does not depend on the magnitude and the direction. When the resistivity of the material does not depend on the resistivity of the material does not resistivity of the material does not depend on the magnitude and direction. Depend on the magnitude and the direction. Okay, the magnitude and the direction does not depend on the magnitude and direction of the applied electric field of the applied electric field of the applied electric field. Okay, applied electric field. It is clear. So that's the temperature coefficient resistance. What it will be? What will be the temperature coefficient resistance? Now, in the other form of Ohm's law, the temperature coefficient resistance of alpha. Okay, it is the defined that the charge resistance per unit origin resistance and for the degree rise that the temperature is given by. So the temperature coefficient of resistance, temperature coefficient of the resistance. Okay, so what it will be the temperature coefficient of resistance? What? Listen. So the temperature coefficient of resistance, it is defined as the change in resistance. It is defined as the change in resistance. Okay, it is defined in the change in resistance per unit original resistance per degree per unit original resistance per degree original resistance original resistance per degree rise in per degree rise in temperature. Okay, so temperature, it is given by alpha is equal to R2 minus of R1 divided by R1 into T2 minus of T1. Okay, T2 minus of T. If T1 is equal to 0 degree centigrade, okay, and T2 is equal to T degree centigrade, then alpha is equal to alpha is equal to R2 minus of R0 divided by R0 into T. Okay, or it's depend that or RT is equal to R0 into 1 plus of alpha T. 1 plus of alpha T, it is clear. So the unit of alpha is, so the unit of alpha is centigrade inverse or Kelvin inverse one. This will be the ultimate answer. Ultimate theory. Okay, so effect of temperature in the resistance. What will be the effect of temperature if in the resistance will be different? So the effect of temperature on resistance. Effect of temperature on resistance. Effect of temperature. Effect of temperature on the resistance. Effect of the temperature of the resistance. What it will be the effect? So for metal, alpha is a positive. Okay, resistance of material increases with the increase with the temperature. So for semiconductor and insulator, alpha is a negative, and their resistance decreases with the increases temperature. The resistance for metal, alpha is positive. Okay, so the resistance of metal increases while increase of temperature. The semiconductor and insulator, alpha is a negative, and their resistance decreases with the increase. Alpha for semiconductor and insulator, alpha is negative. Okay, so when alpha is a negative, the temperature coefficient, but temperature coefficient, the temperature coefficient is negative, their resistance decreases with that the increases temperature. Increase the temperature for the alloy like constant, and for the alloy like constant, বলছে constant and margin বলছে managing the temperature coefficient of the resistance alpha is very small, so they are used for making standard resistance. So they are for metal, for metal alpha is positive. Alpha for metal temperature coefficient, temperature coefficient bracket alpha is positive. Alpha is positive. Okay, alpha is positive. Resistance of metal increases. Resistance of metal increases. Resistance of metal increases with the increases in temperature, with the increases with temperature. Increases with temperature. Okay, increases with temperature for semiconductor and insulator. For semiconductor and insulator, what it will be? For semiconductor and insulator, alpha is a negative. Okay, alpha is negative. For semiconductor and insulator, alpha is negative, their resistance decreases. Their resistance decreases with the increased temperature, with the increased temperature. Okay, for alloy,